inviting me, and Jean-Paul and Jean-Bernard. I must say I found the topic of the workshop very exciting, geometric and numerical foundations of movement, but also very intimidating. And, well, because, voilà, il y a moyen de, non, c'est bon? I do have a few gray hairs already, but maybe not enough to speak about the foundations of movement. That's very intimidating. So I thought that maybe I would have a more focused with more limited scope. So I'm sorry, this is the best that I could speak about. So redundancy. And redundancy is the word that has many different meanings depending on who you speak with. So if you open a dictionary, as I did, redundancy is about things being not or no longer useful. So hopefully I'm not going to tell you anything about unuseful things. If you focus about, so what's the meaning of redundancy in robotics, and you have great researchers with impressive contributions like Professor Nakamura, who will speak this afternoon, and basically this is the layout. You want your robot to do something, and maybe some parts of the robots are redundant with respect to this task. So they can be used maybe to do another thing additionally. And then you can iterate. So you can say the robot has to do something, and if possible, maybe do something else as well. And if possible, do yet another thing. The interest I see in this approach is, well, if you go full science fiction, you could consider the 3 laws of robotics as proposed by Isaac Asimov. And you could say, well, I want my robot to not harm anybody. And if possible, I would like my robot to obey my orders. And if possible, I would like my robot to not destroy itself while following my orders and not harming anybody. So it was not stated in that way, it was stated with except. So you should do this except if it conflicts with the first law. But basically, you see here a redundancy scheme. So you see, of course, this doesn't solve all problems that you are going to encounter. And basically, that was the fuel of most, if not all, the novels written by Isaac Asimov, which were about where does that fail. Okay? But still, I believe there is something interesting to consider here, which is that redundancy is about making decisions. So you want a robot to do this and that. And what if you cannot do this and that at the same time? You have a conflict, so you have to make a decision. And those decisions will be often related to safety. I want to do this and that, and you have to make the choice which makes your robot safe and make sure about that. So of course, this was science fiction. And as commented by another science fiction writer who was mocking gently Isaac Asimov, today's robots are very primitive, capable of only understanding simple instructions such as go left, go right, build car. So that's exactly what we do usually. Go left, go right. Build car is another story. So the most usual use of redundancy is kinematic redundancy. So for example, we want our humanoid robot to maintain its balance first, because if it begins falling, it can be very dangerous for itself and for the environment. And if possible, we would like maybe the robot to also avoid hitting the environment, colliding the environment. And if possible, we would like the robot maybe to do something useful, like grasp an object. And if possible, in the case that I'm going to show, well, maybe keep looking at the target just to be sure that you catch it. So I'm going to show you a simulation which was realized by Usama Kanoun, who was a PhD student here. And he just does that. Maintain balance, avoid colliding the bars here, grasp the object while trying to keep it in sight. And you can see that he tries to balance all those objectives, but in the end, he cannot, and he has to make a choice. He cannot keep looking at the object while avoiding collisions and grasp the object. and it has to deal with the conflict between those objectives. And here, we design very clearly that, well, it should grasp the object and maybe not look at it anymore, because that's more important. But collision and collision avoidance balance are more important and should not be discussed here. So what's interesting is that in case of conflict, priorities are enforced at least as defined. So you have other uses to redundancy. Another one is force redundancy. So just to show another example, here our robot should maintain its balance as before, grasp an object, and maybe use only specified contact forces. So that's for example, you have a plan. You want your robot to get out of a car as it happened, and then you make your plan, and your plan tells you should use this contact and that contact, etc. But then what happens if you cannot follow the plan and you cannot satisfy all this? Then you have to make a choice. And here the choice would be, well, use additional contact forces. That's not so important. And here, this is a simulation that we published at last Humanities conference. You have the robot who has to grasp the object, and here you have a contact which was available, but we said to the robot, you shouldn't use it if you don't need it. And you could see in the beginning of the motion, it was not using it, but after some point, it needed to use it. And then when the target moves back, it can reach it and not use this contact. So you have this decision making which is done online, which is, well, depending on the situation, you will use this contact or not. So these are rather usual uses of redundancy. Another one, which is less frequently discussed in robotics, is time redundancy. You want to do something, but you can use some time, or time can be used in different ways. For example, you want your objective maybe to be realized now and later, but maybe you can't do both, and maybe you have to make a decision. And we have been playing with this idea and really meeting all those three options. The one is, well, at least you should do it now, and if possible, you might do it later. That means, well, do it as long as possible. Or the other way around, at least I want this to be achieved later, and, well, if possible, do it as soon as possible. And sometimes you don't want that, and we meet such occasions. Sometimes you just want to say, well, now and later are equally interesting. If you can't do both, try your best on both. Okay, so we have different options for different situations. So another example here, it's a manipulator robot, or a pair of manipulator robots, in fact. They should avoid collisions, because these are dangerous. They should, if possible, not accelerate too strongly. So, of course, you don't want to burn your motors, but that comes as a second priority. Well, the first one is really avoid collision. So that means we are ready to burn the motors if you at least avoid colliding the other robot or a human in the environment. And if possible, you want to reach the target. And you want to reach it as soon as possible. So here what that means, I want to reach the target in 10 seconds. But if possible, I want to reach it in 9. And if possible, I want to reach it in 8 seconds. So you have this kind of list of priorities. And you can do that. So it's a paper we submitted, so it's not published yet. That's what we call a hierarchical approach to minimum time control of industrial robots. And have this working, if the video starts. You have the two manipulator robots, and they have to reach the target and in minimum time. And they do this online control of reaching the target as fast as possible. So here you have, they go as fast as possible. You have other kinematic, so the hardware could go faster, but there are other limitations on the control system. So you have somehow this decision. I see this as a decision of, well, I'm going to reach the target in this amount of time, depending on my other constraints, collisions and constraints on my actuators. So in the end, our robots, what we want them to do is, generally speaking, tackle complex situations safely. And what does that mean? That means that we want our robots to do lots of things all together. And you want to throw all those things, all those requirements at your robot, but then you're going to have conflicts with them. And it is important that the robot deals with those conflicts in the best way. And I'm a strong contender for online problem solving. And that's why I was asking yesterday questions about planning or learning, because you cannot pre-plan, you cannot learn everything, I believe, but that's something I'm always open to discuss. And so here what I try to work on is, well, you give a general rule, a general way of solving the problem, but the robot, you never know in advance which kind of conflicts is going to happen, and you want to solve them online. So basically, situations of conflict are when behaviors become interesting, because that's where the robot has to make a decision. It cannot do everything that you want it to do, it has to make a decision. And especially, it can have to make important decisions because these might imply safety. So conflicts are the interesting things here. So in a way, the title of the talk could have been Geometric and Numerical Aspects of Conflicting Objectives. And I'm focusing now on those conflicts. So now I'm going to speak about geometry and numerics. So the standard approach to kinematic redundancy, that you open any textbook from 3 decades ago, you have this kind of definition and analysis. Let's say we have 2 joints on our robot, rotating joints. We have a planar robot, so you have 2 angles, θ1, θ2, and you want the robot to reach some given x position with the end effector. So you want to constrain θ1 and θ2 with such an equation, cos θ1 plus cos θ2 equals some desired position. The analysis of this, using tools from differential calculus, implicit function theorem, you can put it differently, but basically amounts to looking at the differential of this constraint. So here you would have this Jacobian, it's just a gradient, but it's a Jacobian involving the sinus of the angles and the joint speed. Okay, and then you can say, well, you know, I have 2 degrees of freedom, I constrain only in one direction of the motion, so I still have 1 redundant remaining degree of freedom that I can use to do something else, like controlling the y position, for example. That works very well, except when you begin to reach the limits of your system. If you want to control x to be exactly here, in that case, your equation becomes, the derivative becomes singular. The Jacobian here is just 0. Okay? What appears here is that the linearization is not appropriate at singularity. And that can lead to difficult questions. So the solution to this problem appeared quite quickly, and it was strikingly simple and very efficient. Avoid singularities. Okay, and that's what everybody does, basically. You just avoid singularities, and then you can use your linearized model, and it works, and you're happy. However, in the case of those redundant problems, redundancy solving problems, we have to deal with singularities. So, for example, Tomomichi Sugihara in a paper in IROS, just in this paper, there's just 1 sentence mentioning this. The fact that basically in these kind of problems, here it was a problem of inverse kinematics, but with some different hierarchy of priorities, usually it deals with unsolvable systems, and the solution is often found at a singular point. You can analyze this more mathematically. For example, if I have those 2 equations that I want to satisfy, I want g to be equal to 0, I want f to be equal to 0. Okay, so my priority here is that g should be equal to 0, and I would like, if possible, to have f equal to 0. I can cast this as an optimization problem, a constrained one. I constrain g to be equal to 0, and I would like to minimize the norm of f. And if possible, it is equal to 0. If I have no conflict, it is equal to 0. But if I do have a conflict between those 2 things, I will not manage to have f equal to 0. F will be different from 0. Now, if I look at the optimality conditions, here you would have f transpose the Jacobian of f, and there you would have Lagrange multipliers multiplying the Jacobian of the constraints. And you can see that if f is equal to 0, I have this equal to 0, and you can just choose 0 Lagrange multipliers, and you're happy. The optimality conditions are satisfied. You have nothing more to discuss. But here, if you have a conflict, then this is different from 0, and you might need also some Lagrange multipliers different from 0. But basically, what you see is that you have some linear dependency in the Jacobians, either only in the Jacobian of f or in the Jacobian of both f and g. Okay, so you have, as soon as you have a conflict, you have linear dependency. So some people are sometimes criticize this approach of using a constrained optimization problem and prefer to discuss weighting those two objectives. You could say, well, I want to minimize both f and g to 0, but I'm going to weight. If I cannot have both equal to 0, I will try to have both close as possible to 0. And then you can use some weight omega. But the situation is basically the same. If you look at the optimality conditions, these will be the optimality conditions. So if you have no conflict, it means that you will reach f and g equal to 0. Your optimality conditions is trivially equal to 0. You're happy. But if one of them or both are different from 0, then you will have some linear dependency appearing here again. So it's not a question of using an unconstrained scheme or a constrained scheme. As soon as you have a conflict, you have linear dependency. Okay? And by the way, just noting here, if you increase omega, so the weight that you put on g, and make it grow without any limit, you will put more strength on minimizing g, and you can see here that g would go to 0 while omega would increase, and in fact the limit of this will be exactly the Lagrange multiplier here. So you can show here, for example, very easily that the limit of weighting is the hierarchy, and I'm going to mention that later. But basically here what we can observe is that situations of conflict are not only interesting and important, but that's where we have problems. That's where we have linear dependency. There is the relationship between linear dependency and singularity is a little bit subtle, but basically here that means singular in all the cases I was showing. So let's see what what happens with the simplest example possible. We have just two objectives assigned to our robot. This is a manipulator robot. I want to grasp an object. And if possible, I want to not move. Okay, so if the object is here, grasp it. If it's there, well, you cannot do both, but, well, grasp the object, and you don't have to stay there if you need to move. So we did that. We did try to ask our robot to do that. Catch the glass which is there. What the robot happened to do was raising the arm, shaking the arm because you reach some singular situation, but not moving, which was, of course, not what we wanted, which was frustrating. So trying to analyze that, here you could have the most simple template for this, which is I have a 2-degree of freedom robot. I have a mobile base which can move horizontally, and I have just one joint moving vertically. And what I want is that the position of this point to be on this line. So I want x plus cos theta equal to 2. So I define g as 2 minus cos plus x plus cos theta, and I want this to go to 0. And then my second objective was, well, and if possible, do not move. If possible, keep x, the position here, to 0. What you can see here is that, quite naturally, if you are in such a situation, at least locally, you can try to improve on both objectives at the same time. But what that means is that your base is moving backwards while your hand, your effector is moving forward. Okay? And the robot will be very happy doing that. It satisfies both of your objectives. And basically, when you are starting here, it will just stay here, and then because it's happy that, my hand is moving toward my objective. And then I reach singularity, and because singularity is a problem, usually it begins shaking. And it's only when it manages to really reach the singularity that suddenly those two constraints become conflicting, and then suddenly it says, oh yes, now I can move. So in the end, the robots sometimes manage to do what we want, but in a completely an interesting way. First moving the hand and then only moving to the target. And that's not what we want. So it behaved somehow as designed. It was not a bug, but it was a design bug because that's not what we wanted. So in order to analyze that, we began focusing on the task space. So here, this is the space where I represent f and g. And I want both f and g to be equal to 0. Basically, I would like to be here. Okay? But there is a constraint. Because of the kinematics of the robot, this is not possible here. And basically here you have you can see that if you sum f and g, you take the sum, f plus g is 2 minus cos theta, and it's always greater than 1. So you have a kinematic limit, which is here. You cannot reach this point. And basically, if you want to, for example, get as close as possible to this point with some weighted norm between f and g, you would take the closest point with some ellipsoidal norm, and it will tell you when I want to be here. And if you vary omega, you will want to be here or here or here, depending on your norm. And if you take the limit of increasing omega, you will reach this point. And basically, if you consider the constrained approach, it tells you I want to be, for g is equal to 0, so I want to be on this line, and I want to minimize f squared, so I want to be here. So basically, what you see is that all your solutions, whatever the cost function you consider, whatever the approach you consider, all your solutions are on this line, on the limits of your reachable set. And the point is that all this line is in fact all the situations where the Jacobians become singular. You can see that when you are here, you are in this situation. The gradients are linearly independent. When you are here, all those points here correspond to this situation where you have this singularity. And basically what happens then is that when you are here, in all this space here, what you would like is f go to 0, g go to 0. So you would say, I want delta f is equal to minus alpha f. I want delta g equal minus alpha g. And delta f and delta g can be related to your joint motion through the Jacobians. And the Jacobians here, there is no conflict. They are linearly independent. So you can solve this exactly. So you can have exactly delta f equals minus alpha f, delta g equals minus alpha g. Which means that when you are here, you are converging in this direction. And you are very happy with that. And it's only when you reach the limit that suddenly your constraint, your two Jacobians become singular, and then suddenly the robot realizes, oh, well, I have to make a choice between f and g. And in that case, I will satisfy g is equal to 0, and I will move here. So you can see here that you have this, in this space, you just happen to not go in the direction that you want because you want to go here, but you basically follow what you designed. So basically what that means is that the linearization is not appropriate. Why is it not appropriate? Because the solutions lie on this singular manifold where the rank is different from the rest of the space. Here I have rank 2, here I have rank 1. So the linearization here is not appropriate with respect to finding a solution here, and it's only when you reach this singular manifold that suddenly your linearization is correct. So how can we tweak this? How can we say when you are here, no, try to go in this direction? Hopefully, we tried a method which is known in numerical optimization, which is trust region methods. Basically what you say when you consider the linearization of your problem, which is I want to satisfy g converging to 0 and then minimize f as much as possible, well, at least what you should consider is maybe bounding the motion of your robot, so the step that you're going to realize. But what is important is that this step should be adapted as needed. And it can be an intricate question, how do you adapt this delta, but there are rules proposed in the literature. So the idea is to limit the size of the step. But what was important here is that, you see, if I just, for example, change alpha, I just make a smaller step, I still go in the wrong direction. So it's not just a matter of making a smaller step. What's interesting with stress region methods is that by reducing the size of the step, they alter the direction. They modify the direction in which you go. And here they modify this direction in a very interesting way, because what they do is that you have this additional constraint now, and depending on the size of delta, you might either be able to satisfy f plus delta plus j delta q is equal to 0. So you would satisfy your both constraints and you would go in this direction. But if you limit delta, you are going to have a conflict between this and that. And because of that, you are not going to satisfy this constraint, this objective anymore. So the interesting thing is that by bounding your step, you discard somehow the second objective and you put more emphasis on the first objective. And because of that, you happen to go more in the right direction. And I was quite surprised it worked, and for that reason. That was really understanding how it works was illuminating. So just mentioning one comparison is that if you consider the weighted approach, and you can work just as well and bound your step, and basically there is an equivalence, which is a well-known equivalence in numerical optimization, with the fact that instead of bounding this way, you could penalize, and you have a direct relation between how much you penalize and how much you bound. So basically this looks like dumping. But there are two important facts, two important differences to respect to what we usually use, how we usually use dumping. First thing is that, well, you need to adapt online how much you dump, and you may need huge dumping, because what you want here is that by bounding, you want to cancel somehow one of your objectives. So here you would like lambda to be greater than 1. You want your dumping to be greater than 1, because you don't want to realize that. You want to focus on this, with omega, for example, being 1,000. Okay, so we use dumping here to really modify the problem. Usually in robotics we say we use dumping because we need, but the comment is that, but we don't go in the direction that we want. But here, the linearization doesn't give you the direction that you want. You want to modify this direction. So basically what we do is that either considering the constrained approach or the unconstrained approach, you linearize your problem, but you have to modify it with a trust region approach, adapting those lambda or delta in order to make it work. Just a side note, so here we happen to solve then a sequence of linear problems and iteratively, and just two details. In solving these linear problems, it appeared that the constraint approach usually is discarded because people usually believe that it's more complex to solve. In fact, it's easier and faster to solve than the weighted case, even though when you write it down, it looks more complex, but it's faster to solve. So there is some misconception here. But still, there is a lot of work to have it work, to make this approach work, because you have to handle semi-definite QPs, and that requires to be very precise in what you do. So wrapping up and discussing this, I've been discussing here mostly the numerics related to geometry. Going back to the geometry, we have this state space. Now here it's the task space. And you can see that depending on the region where you are, the rank changes. And depending on where your goal is, you will have a goal which is here, or maybe a goal which is here. If you want to grasp your object and it's within reach, you have no conflict, you have rank 2. So the rank of your objectives changes depending on the exact setup, and you have to adapt to that. But even more interesting is that the number of degrees of freedom is not strictly related to the rank. So usually you consider this kind of setup. So here I just added more degrees of freedom to my system. So, and I want x to be here, and I want x plus cos theta 1, cos theta 2, etc. to be here. So I have two constraints on my system. I have n degrees of freedom. Those two constraints fix 2 degrees of freedom of my system, and I can use all the other to do whatever I want. But when you have a conflict between those two when you reach singularity here, I want x to be here and the sum of the cos theta to be here. My constraint becomes singular. I have only rank 1 for my 2 constraints, but I have a unique solution with the 6 degrees of freedom are constrained. Okay, so in this singular manifold, all the rules that we are used to discuss in robotics are wrong. So, in summary, I believe redundancy is a very interesting question to discuss. It has a lot of potential, I believe, for safety and online decision making. But we do have to face very unusual geometric and numerical behaviors. We can use linearization, but it has to be changed. You cannot use it right out of the box because it may not be appropriate depending on the exact setup. And since you don't know in advance, you have to alter it with online adaptation. So we have a solution, and so far it is working reasonably well, but there are lots of questions, other questions to discuss. Some of them I decided to skip for this talk, like constraint qualification is an important one, and equivalence between various formulation and optimization problems. And some of them, we don't know yet the answer. So, of course, this work, I didn't do it alone. It was a collaboration with some of my students and also with Adrien Scand, who is here. So if you have questions, he might have different answers than me to give. So it can be both answering those questions. But let me end with this note. We observed at some point that the robot behaved as designed, but not as desired. There's the whole question of, well, what is it that we want? And what is the mathematical formulation to obtain what we want? Okay, and that's a modeling problem, and I believe that's one of the strongest problems we have. Of course, when you have a mathematical problem and have to solve it, it can be hard. But at least you have tools, numerical tools, and you have theories to help you. But defining what is it that you want usually is done iteratively. And basically, that's what we did in many occasions. In the examples I showed you, we try some model, and it just doesn't do what we want. And I showed you here an example. And then you have to modify it again and again. And at some point, it gives you what you want. So this modeling problem is a really important one. And how do we know what we want? Basically, usually we don't know. We just observe. And then that raises a question. How do humans tackle such situations? And there you have the question of reverse engineering and finding what is this optimal problem, if there is any, that the humans are using. And that's one of the interesting questions I believe in this field. Thank you for your attention.
Just a remark before starting the question. To say I agree very much with the last point. I think that the behavior of human or of any system depends a lot on the methods that is used to solve the situation. Except in singular points, where, well, a singular point is something that is very intrinsic. It's pretty much non-depending on the algorithm that is used to solve. So I think it's very interesting to study the singular points of behavior. And I'm not aware of so much work on human study on singular situations.
Exactly, and that's something I would see people analyzing the impedance in humans, for example, tell us more about, but how do humans work at singularity?
Yes, more comment on question. Because, yes. Yes, it works. It's my fault. Okay. And yes, yesterday I explained that geometry is formulated by groups. And groups, it appears exactly in the same situation 2 centuries before, because people try to solve algebraic equation, and they try to understand the solution by force. But what inventor of groups is Galois, and he understood that it is much more profitable to look at the ambiguity between the solution, which have structure, and mainly the structure he got, where by reflecting how I specify a solution now if I add some information of them. Okay. For example, in this case, it was to put a new number to the rational field.
Mm-hmm.
But it's just a comment that perhaps it's the first step to geometry in you.
Mm. Thank you.
Your comment about humans and singularity, I
Yes.
don't know if this is relevant to what you were asking, but for example, during locomotion and stance, we operate with the legs precisely in a singular configuration for energetic reasons. And we do that all the time.
Yes, but how do we
Well,
manage that?
Well, one of the, for example, humans walk with much straighter legs than any other biped, including robots and chimpanzees.
Mm-hmm.
And one of the tricks that we use to avoid the impact that happens when you, to avoid transmitting the impact through the singularity, you set up the mechanical impedance of the ankle to pull the knee out of singularity without voluntary control. You basically use the fact, your heel projects further back than it does in a chimpanzee or a bear, and that pulls your foot down and your knee forward. So you can set up the intrinsic biomechanical behavior to let you stay in the singularity when you need to, and get out of it when you need to. But I don't know if that addresses your...
And maybe you could see this as a form of adapting the dumping somehow. There might be a connection there.
There should be.
Yeah,
I don't know.
probably. Yeah, thank you.
Thank you. Yeah, I just wanted to follow up on the singularity thing as well. Just make an observation and perhaps ask you, did you say at the end you hadn't touched on the link between Bayes formulations and your... Did you say Bayes or something else?
Bayes?
No, you didn't. Good. Okay. Bayes. Bayes. Oh, I see. Right. Okay, well, I've sorted that out now.
Okay.
It just struck me that your formulation of the multiple constraints in terms of weighted cost functions was formally very similar to putting prior beliefs on preferred outcomes, and that the singularity, the adding of the damping term was to preclude singularities. And in a Bayesian perspective, those singularities basically mean that your Fisher information matrix from the information geometry perspective is zero. So from the point of view of a Bayesian agent, what you're saying is it will not sample situations or put itself into situations where there's no mutual information between its behavior and its outcomes. Put another way, it believes it should avoid non-salient sort of spaces.
Yes, indeed.
So I think it's a very nice connection between the sort of the nastiness of singularities and the collapse of the information geometry.
Exactly.
Points, yeah.
Exactly.
Maybe by definition, a singularity is a point of measure null, so you cannot sample it. Last question before the next one.
Maybe a naive question, but is it true that most mechanisms have always never a second order singularity in the Hessian, like?
So it's. I haven't spoken here about the second order information of the model. It can sometimes save you because sometimes it's not singular, but sometimes it is singular. And basically, in the case that I was showing, it is singular also.
But wouldn't the method fail as well as the linearization if the second order is also flat?
Exactly. So you do have. So just introducing the second order information can help you a bit, but not in all situations. But hopefully here, see, I was not discussing the second order information, but it is important to take it into account when it works because it helps a lot. But disregarding the question of the second order information, here the important thing is that by bounding the steps that you make, you discard some part of your objectives, and that was the message I wanted to propose.
So let's thank the speaker again.